Hi everyone. Hope you are all doing well and staying healthy during this unusual time. Today, I will be talking about a combination of two interesting topics in computer science: quantum cryptography. Current cryptographic protocols like RSA work now, but we will discuss how quantum computers will crack encryption methods like RSA easily, forcing new quantum protocols to take place. First up, let's refresh on cryptography basics. Key-based cryptography can be divided into asymmetric and symmetric protocols. The main difference between these two is that symmetric cryptography uses a private key that both sender and receiver use, while asymmetric requires both a public and private key. A common asymmetric method is RSA, which we will discuss in greater detail in a minute. AES is a standard symmetric procedure. It is so strong and hard to break that it is used by both governments and well-known companies like YouTube. It takes the shared key and shuffles the bits in a particular sequence dictated by the protocol. Since AES is not the focus of today's discussion, I will not be going into further detail. However, there are plenty of great resources about AES, such as PBS Infinite Series, if you want to learn more. Why then is RSA even used if AES works so well? The problem is that AES uses a shared private key, which must be agreed upon in advance to the transmission. In many cases, we use RSA protocol to make a secret key, and then use that key to encrypt messages following AES protocol. So if quantum computers can break RSA, they make AES vulnerable as well. Since RSA protocol is relevant for both asymmetric and symmetric encryption, let's take a closer look at it. For asymmetric keys to be successful, they have to be fast and easy to make, but hard to break. We accomplish these objectives using a one-way function. Multiplication is the one-way function for RSA protocol. Multiplying two numbers together, even really big ones, is easy for a computer. But factoring large numbers like this is a different story. The first step in RSA protocol multiplies two extremely large prime numbers, p and q, to produce an even larger number, n. P and q are typically hundreds of decimal digits long. Since you know the two factors of n, you can also produce another two numbers, e and d, such that m to the e to the d power equals the original number m mod n. The public key in this example is n and e published together. The private key is d, and m represents the message. This system ensures that encryption is relatively fast and decryption is slow, because the only possible way to reverse engineer the private key d is to know the prime factors of n, p, and q. As of this moment, this process takes computers a seriously long time. The complexity of such algorithms are not polynomially bounded. However, one thing that quantum computers can do quickly is factor really large numbers, which is bad news for RSA protocols. Quantum computers are able to do this using Shor's algorithm, which goes like this. First, we pick a number a less than n. In this example, I chose a to be 8 and n to be 35. Next, we must find the period r of a to x mod n. To do this, we find the first power of a, where the remainder of a to the x divided by n equals 1. In this example, 8 to the fourth power is 4096, and 4096 mod 35 is equal to 1. So r equals 4. This is our period. We then check that r is even, and that a to the r divided by 2 plus 1 is not evenly divisible by n. In this example, r is 4, and so it's even. And 65 is not evenly divisible by 35. Finally, we solve for p and q using the greatest common divisor. These are your two factors. In this example, we get p to be 7 and Q to be 5, which is correct. Steps 1, 3, and 4 are relatively quick. The part that makes this computationally expensive is step 2, finding the period. On a classical computer, finding the period in a reasonable time is nearly impossible. On a quantum computer, however, a quantum Fourier transform makes the complexity of this process polynomially bound, threatening the integrity of symmetric protocols. Therefore, quantum cryptography is necessary to maintain the security of the future quantum internet. The good news is that methods to do so already exist. Today, we will focus on 2 quantum key distribution procedures that take full advantage of quantum properties, like the Heisenberg uncertainty principle and quantum entanglement. To demonstrate these concepts, let's use the polarization of a photon. Photons are ideal quantum particles because they can be transmitted via fiber optic links, a practical medium for quantum networks. As you can see, in the rectilinear basis, a quantum computer interprets vertical polarization as the 0 bit and a horizontal polarization as the 1 bit. Meanwhile, a diagonal basis represents 0 as a photon with a certain diagonal polarization, shown on the bottom row in the middle, and a 1 as a photon with the opposite diagonal polarization. However, the Heisenberg uncertainty principle prohibits the observer from measuring the polarization both ways. If the observer measures the photon using the rectilinear basis, all information about the photon's diagonal polarization is lost. Here's a visual of how that works. Say I'm measuring this photon with a vertical polarization filter, like this. All of the diagonal light waves cannot get through the filter. However, if we measure the photon polarization diagonally, the vertical light waves would be blocked. It is impossible to measure both vertically and diagonally because these slits can only face one way. The first quantum key distribution protocol we examine is BB84, which applies this concept in a symmetric encryption scheme, which means they have the same key on both ends. Let's see how this works in greater detail. Say Sam wants to send Alex a message. First, Sam generates a random string of bits encoded as photons, each polarized in either the rectilinear or diagonal basis. She then sends that string to Alex over a public channel. Sam and Alex then choose a random basis to project their photons onto. We then inspect the basis used for each corresponding photon and the result of each measurement. If the same basis was used, then the result of the measurement will be the same. If not, Alex will get a different random result. After that, Sam reveals which basis she used and the bits she originally sent. For each photon, if a different basis was used, Alex can disregard the result, but if the same basis was used, then the answer should be the same, 1 equals 1 and 0 equals 0. If the same basis was used, but the result is different, then there must have been someone snooping in on their transmission. Matt, the man in the middle, correctly guessed the first 2 bits that should match, but wasn't so lucky for the other 3. Look at the last row, for example. Sam used the diagonal basis and measured it to be the 0 bit. Alex measured the photon using the same basis, but received a 1 instead. This inconsistency was caused by Matt measuring the photon with the rectilinear basis, tampering the transmission to Alex. On the other hand, if the test passes, Sam and Alex can keep the matching measurements as their private key and discard the rest. They are then free to transmit their message using a symmetric encryption method like AES. Unlike current methods, This application of AES does not rely on protocols like RSA to make their private shared key. In other words, no factoring is involved, so it's safe from quantum computers. The only way to crack BB84 is to guess the exact combination of bases, which is virtually impossible considering that Matt only has one chance to do this. The other quantum encryption scheme I referred to is Eckert's protocol. It is similar to BB84 in that it also uses the choice of quantum basis mechanism. It also applies quantum entanglement via Bell's inequality. Entangled particles measured in the same basis always have opposite spins, like shown. For example, if I measure an entangled photon to have a vertical polarization, its entangled partner will be measured to be horizontally polarized. However, any measurement in between disentangles the particles. Let's go over a concrete example to show how this protocol works. This time, Liana wants to transmit a secure message to Jackie. First, Liana generates a set of entangled particles, meaning they will have opposite spins. She then sends half of the pairs to Jackie. Then, Liana and Jackie choose a random set of bases to project their particles on. Once Liana and Jackie measure using their respective bases, the particles become defined. They choose whether to be vertical or horizontal, as well as what direction they will face. If they choose the same basis, they should get opposite results. The pair are entangled, so Bell's inequality dictates that if one particle is measured to face up on a vertical basis, then its pair will be measured to face down if projected onto that same basis. If Liana and Jackie choose a different basis, then they can disregard these measurements just like in BB84. So what happens if Vanessa, a man in the middle, listens in on their transmission? If Vanessa makes any measurement, she will disentangle the particles, and Liana and Jackie will be able to tell that their message was intercepted because the particle pairs measured with the same basis no longer have opposite spins. Notice how the third particle pair is projected onto the same horizontal basis, yet do not have opposite spins. Jackie's particle should be pointing left if the particles were still entangled, but it cannot even be measured using the horizontal basis. It's facing vertically. Now the ethics. Considering that quantum computing is quite expensive, and sensitive data is currently protected using RSA schemes that are vulnerable to quantum computers, governments are at the forefront of quantum cryptography research. We must ensure that when quantum computers become common in the private sector, that governments are not abusing their knowledge of quantum networks and encryption schemes to illegally spy on citizens and their private information. In other words, we must make sure that these protocols can even protect against government surveillance. Don't get rid of classical computers yet. As quantum computers become more prevalent in our lives, where do classical computers fit? As previously mentioned, we can use a hybrid scheme, a combination of quantum and classical encryption methods. We still need classical algorithms to prevent hackers from impersonating receivers in a network using BB84 protocol. In addition, quantum computers will not entirely replace classical ones either. Talia Gershon, the senior manager of quantum research at IBM, foresees classical algorithms making calls to quantum computers to do computationally intensive work. There have also been attempts to create encryption protocols that do not rely on factoring, and are therefore not susceptible to Shor's algorithm run on quantum computers. IBM has developed crystals, a method based on lattice problems. The one-way function for this algorithm is adding a subset of numbers together to encrypt. To decrypt, the receiving party must simply say which numbers form the subset. This problem is very difficult to break, especially if the numbers are incredibly large and the size of the set is also very big. Still, quantum cryptography will play a large role in protecting against hackers utilizing the power of quantum computers. These are my references. You can check out these videos and articles if you want to know more about quantum encryption. You can also contact me